Hey, welcome to another exciting episode here of Advanced Level Chemistry at Spain Park. Today is Thursday, November the 14th, 2024. And today we're going to be talking more about the quantum numbers and electron configurations. So Jack, what are they supposed to do if they're liking these videos?
Smash that subscribe button, ring that notification bell, and don't forget to click that like button.
Click that like button. Here we go. All right, so here is our bell ringer question to calculate the energy and wavelength and frequency of a photon emitted when an electron transitions from the sixth to the third. So whenever we have to calculate the energy, we're going to use this equation. Now all of this is going to be given. So we're going to say it's always going to be final minus initial. So delta E is going to equal our final negative 2.18 times 10 to the minus 18th joules divided by the final, which is 3 squared, minus negative 2.18 times 10 to the minus 18th joules over 6 squared. Final minus initial. Okay? A lot of people get it backwards. If you do it backwards, you're going to get a positive value. If you get a positive number, that's the energy of the photon needed to take it to go from the third up to the sixth. Okay, that's what Alabama Power does. They supply the energy, but all energy is transferred to and from matter in the form of photons. So this all turns out to equal what number? Negative
1.82.
1.82 times 10 to the minus 19th joules. So what again does the negative sign tell me?
You lost
Energy was released. So it's when the electron comes down is when it releases the energy. Okay? It's just telling me the direction of energy flow. What is that the energy of? One photon. One photon. Now you got to realize if you're having a hydrogen atom, you're going to have a bazillion photons in there. Okay? A bazillion atoms with a bazillion electrons going up and down. And so those electrons there, Alabama Power keeps pushing them up, or we stick it in a fire, or we have it in the tube and we turn the electricity on. The electron goes up, it comes back down. You have a bunch of them doing that, and any single electron can go up and down, popcorn, back and forth, back and forth, back and forth, because every time it comes down, another photon hits it and it goes back up and back and forth. So we're constantly seeing this. So that's my change in energy. That was what I would say the answer to part A. Part B, now I need the frequency. So what equation am I going to use to calculate the frequency? E equals h nu, because that's my frequency. So E equals h nu, doing the very complex math, solving for nu, what's nu going to equal? E over h. So h is always Planck's constant, which is always going to be given. So it's going to be now look, this negative sign only tells you the direction of energy flow. You will never have a negative frequency or a negative wavelength. So at this point, you just drop the negative. I know in math that's a cardinal sin. But here, the negative sign, you have to understand what it's telling us. It's just telling us the direction of the energy flow, that it's exothermic, that the energy is being released. So that energy is going to travel in a certain wavelength and frequency. Wavelength and frequency are going to be positive always. So we're just going to put in the 1.82 times 10 to the minus 19th joules divided by 6.626 times 10 to the minus 34th joules seconds. And notice that joules cancel, and that's going to leave me with 2.75 times 10 to the 14th per seconds. But the question asks for it in hertz. Well, how does a per second relate to a hertz? It's the same thing. So it's 2.75 times 10 to the 14th hertz. Okay? Now, I'm just kind of making a point on that. I really don't care if you just leave it per second. And then C is going to be the wavelength. Well, C is equal to lambda nu, so what's lambda going to equal? C over nu. I know it's easier to say V, but it's actually a nu. So we're going to get 2.998 times 10 to the 8 meters per second divided by the frequency I just calculated, 2.75 times 10 to the 14th per seconds. Seconds are going to cancel, and this comes out to 1.09 times 10 to the minus 6 meters. That's the wavelength in meters. But we're going to calculate the wavelength in nanometers. So we've memorized that how many nanometers are in a meter? 1 times 10 to the 9th. So we can make it easy. We can say 1.09 times 10 to the minus 6 times 10 to the 9th nanometers for every 1 meter. So minus 6, when you multiply exponents, what do? Add them. Again, this is why you take a math class. So you can apply it to a real situation. Math is a tool that scientists create to be able to do real problems. Okay, so exponents, you know this, so when you have a real problem, you can do it. And so you end up getting minus 6 plus 9 makes a plus 3, which means it's going to be 1,090 nanometers. 1,090 nanometers. Now, just for fun, we can see (400 nanometers to 700 nanometers. This is visible. Okay? That's visible. Now, okay, y'all all just kind of always got something going on back there. So, I mean, both of y'all have kind of moved. So if I need to rearrange again, okay, we can. Now, which side of this is violet, which side of this is red? Nash.
The lower side.
Is what?
Violet.
Okay. Which makes this the red. So the longer the wavelength, the lower the energy, right? So now, if I'm at 1,090 though, where am I on the electromagnetic spectrum?
Way above. Infrared.
I'm going to be in the infrared. I'm going to be on the other side of red. I'm at infrared, which is a heat wave. So when electrons going up and down, this giving off photons that we would perceive probably as it's getting hot, not something that we'd be able to see. All right? But all energy is absorbed and released in the form of photons. And they're all going to have the same energy, wavelength, and frequency. We can calculate them all. Now, on the worksheet that you did for homework, energy was given. So you just had to kind of use these two. But here, you're going to have to be able to do this other part as well for the test, which will be sometime midweek next week. Okay?
Can it not be on Tuesday because I have a quiz in like almost every other class on the same day?
It's probably not going to be Tuesday.
Okay, good.
Can we do it on Saturday?
All right, so we all good? Does anybody have any questions as far as where a number comes from? How do I know what to do? Where to go? Are we all good? Okay, because that's important we know how to do this. All right. So now we need to continue on in our discussion of quantum numbers. Get your brains ready. Get fired up, because we're going to go deep. I thought it was getting hot. Everybody's been complaining about being cold, so I've turned this up. Now it's hot in here. All right, let's get your notes out. And we're talking about the 4 quantum numbers. And this is Schrodinger treating the electron as a wave rather than as a particle. Bohr's model that we just kind of solved everything for was for treating the electron like a particle. But we now know that the electron is a wavicle. It's got wave characteristics too. So we're going to look at this, and it's super complicated, but we're going to try to get through the complicated part and just get to the application part of this, which hopefully is going to be a little bit more straightforward to be able to figure it out. So we have our 4 quantum numbers. Now I'm not going to follow the notes. You're going to have to just kind of, most of the notes are pretty outlined, the 4 quantum numbers, but you can kind of fill it in as we go. We already talked about this one. This is the principal quantum number. And it's simply going to be 1 through 7, and it's going to be a counting number. It's going to be a whole number. This is the exact same thing that we just did with the Bohr model 1, 2, 3, 4, 5, 6, 7. He just calculated in terms of it being a standing wave. Remember when I was doing the standing wave with the spring? There is only certain distances, certain wavelengths, certain frequencies where that standing wave would form. If I didn't have exactly the right rhythm, then there's just chaos in the spring. Well, the same thing is true on this electron. There's only certain distances from the nucleus, fixed energies, that the standing wave can form. And so Schrodinger was able to figure this out. We're looking at the 4 variables in his equation that kind of tell us where the electron's going to be. Okay? And again, if we went to a fancy hotel, 30 stories, and I got a room that was 2312, what's that going to tell me? 23rd floor. I'm going to get off the 23rd floor, and there's probably going to be several hallways. And there's going to be placards that say 2301 to 2310 on down this hallway, 2311 to 2320 down that hallway, 2321 to 2330 or 40 or down this hallway. And so I'm going to be able to just figure out that which hall to go in. Each hallway is going to have a variety of different rooms, and then there's going to be a certain number of people that can be in each room. That's what we're doing with these quantum numbers. It's a quantum code. What energy level is the electron on? That's what N tells us. But Schrodinger found that on each energy level, you're going to end up start having different sublevels. The electron can be held to the nucleus with varying strengths based upon its wave pattern. So we get sublevels. That's the hallway in our hotel. What sublevel is the electron on? This second quantum number tells us which sublevel it's going to be on. And then each sublevel can have a various numbers of orbitals, rooms, places where the electron can be found. And then each orbital is going to have a maximum number of electrons that can go in it. And it's going to be 2. All right? So we're just kind of doing a quantum code. We're trying to figure out where are the electrons around the nucleus. And we're getting these quantum numbers kind of give us that direction. So the first one is the principal quantum number, 1 through 7, which states the energy level. The second one is the azimuthal. And what did I tell you yesterday was the definition? What was azimuthal? Where did I see that? Go ahead.
It was like a GPS system where from space where it uses 3 variables to...
The X, the Y, and the Z to give you a coordinate system in space. So these are telling me how are the things arranged in space. Okay? So, azimuthal quantum number, and again, this is all in the notes. I'm just writing it down quickly. By the way, what time are we out of here? Somebody's got to know already. It's right there underneath Coco. Now, right underneath Coco, right here on the books.
3 o'clock.
3 o'clock, so we got 20 minutes, okay? That's Coco, our pet dog, okay? Azimuthal. So, if, this is L, L can only equal from 0 up to n minus 1. Okay? Again, we're having to limit the energy. This is fixed energy, quantized energy. So L can only equal these values. So if n equals 1, well, what's 1 minus 1 equal? 0. 0 up to 0 means 0. So if n equals 1, L can only equal 0. Only one answer. So, only one sublevel on the first energy level. Okay? L equals 0. 0 is meaningless, really. It's just there's only one answer. Now, when L equals 0, that corresponds, we call that sublevel the S sublevel. The S sublevel. It stands, again, remember, when a spectroscopist looks at these lines, they can tell different characteristics on these lines. S stands for sharp. When electrons transition out of this sublevel or into this sublevel, they give a sharp line here. So that's what S comes from, sharp, coming from the spectrum that's given off. Man, look at me, I'm in a very positive mood. I'm going way uphill, aren't I? Okay. The S sublevel, what's the shape of an S sublevel? Spherical. Okay? An orbital, there's only one room. There's only one room on this first energy level. It's the S sublevel, and all the rooms, all the orbitals, which there's only one, is that spherically shaped. Which means you got the nucleus in the center here, a little dot in the center of this, and so you got electrons going in a standing wave pattern this distance from the nucleus. Now we're going to learn at the very last quantum number, it's going to limit, you can only have 2 electrons in any room. So there's only 2 electrons possible can fit into this orbital. So hydrogen only has 1 electron. So we know that hydrogen's 1 electron is down here close to the nucleus, going in some kind of complex wave pattern. What exactly is the pattern? It's impossible for us to know. The Heisenberg uncertainty principle says we just don't know. We just know the probability it's going to be there. Okay? Helium has 2 electrons. So the second electron can go in here as well. So now it's got 2 electrons, helium. But that's all that can be. There's only one possible answer when n equals 1, only one sublevel. There's only one orbital, there's only one orientation in space that this can be. So there's only one room on that first energy level. Only 2 electrons. So what did you learn in 8th grade? How many electrons can be on the first energy level? 2. Because we can only have 1 orbital. I'm explaining why they say the 2, 8, 18, 32, all of that. We're going to see why that is based on these sublevels. Okay? So the first energy level is filled because we only have this one room. When n equals 1, L can only equal 0, only one sublevel. But when n equals 2, if n equals 2, what can L equal? Well, it can equal from 0 up to 2 minus 1. Get your calculator out if need be. 2 minus 1 equals 1. So it doesn't just equal 1, it equals 0 up to 1, but it's going to be a counting number. Okay? Did they do it right, Jack? Did they do did you get it on the calculator there?
1 minus 10 to the 0.
Okay. So it can be 0 up to 1. So in other words, L can equal 0 and 1. 2 answers now on the second energy level. So what does 2 answers mean? If there's 2 answers, there's 2 sublevels. L can equal 0. L equals 0 still stands for the S sublevel. But now L equals 1 corresponds to the P sublevel. So when we look now, an S is always spherically shaped. But this is a 2S compared to a 1S. Now, again, you know the Russian dolls. You open one up, it's got the exact same size on the inside. Open it up, there's a smaller one on the inside. So we have to go in reverse. We have to somehow in your brain put this on the inside of this one, with the nucleus on the inside of this one. Okay? So we have the nucleus surrounded by this smaller sphere, surrounded by a bigger sphere, but there's a gap in between, a nodal region where there's destructive interference going on, and there's a low probability of finding an electron in between. So we end up having the first energy level right here with my 1s, and then I have my second energy level with my 2s. Now I'm drawing it like a ring like you learned in 8th grade, but it's a sphere. And the electron's traveling in some kind of wave pattern on that sphere, and there's this gap in between where there's going to be a low probability or no probability of finding an electron in this space. It's either going to be here or it's going to be here, my fixed energy levels. But on the second energy level, we can also have a P sublevel. Now on the P sublevel, the electrons are going to be in orbitals, rooms that are shaped like this. What do we call this shape?
Infinity.
No, so I haven't told you the name of this one yet. We haven't got there. Okay, it's called dumbbell. D-U-M-B-B-E-L-L, like a weight, like dumbbell weights, okay? Like, you know, you've seen those in the weight room, right? Where it's this, you have the handle in the middle and they got the weights on the outside. So notice there's nothing kind of in the middle, everything's kind of on the outside. Dumbbell shaped, okay? But notice how it's very axial. So it turns out that when the electrons are in this wave pattern, that they're very directional, so it can be on the X, it can be on the Y, and it can be on the Z. We have three equivalent or orbital orientations in space, X, Y, and Z. So it turns out there are three orbitals on the P sublevel. They're all equal energy, just different orientation in space. Actually, in the next quantum number, it's going to tell us why there's three, but there's three orbitals. They're dumbbell shaped. And you say, Mr. Hobbs, how do they come up with that? I'm glad you asked. And just to make you get a little adrenaline rush, I have to go to a college textbook here to get good pictures. Okay? So when Schrodinger, in his equations, when Schrodinger puts n equals 2 and L equals 1 into his equation, solves it, and then somehow or other, when you get that wave function and you square it, they do this complex math, somehow it comes out to where you get a probability of where the electron could be, given that energy. Each dot represents where an electron could be. And if you remember when we were talking about orbitals on the previous page of notes, it says where the electron density, the probability of finding an electron is high, it's a high electron density, and where it's low, there's a low electron density. So you can see there's a good chance the electron is going to be here more so than it's going to be out here. Where these are all, this is not a whole bunch of electrons, this is one electron of where it might be at any given moment. This is a 2p orbital. So when we look at that, they shape it right here to where there's a 90% chance of finding the electron in that area. How's it traveling in that area? We don't know. Does it stuck in that area? No, it could be out here, whatever. This is just the most probable place to find the electron. But it's just as easily could be here, here, or here. Three different orientations in space that are equal. So in your notes right there where it's talking about P sublevels. Does everybody see the P? You all right there on the P? It says it's dumbbell shaped. There can be three P orbitals. What does it say about energy? Does it say anything about energy? Only on, where was the first energy level it started on? When's the first time L can equal 1? When's the first time that L can equal 1? What does N have to equal for L to equal 1? 2. So it starts on the second energy level and above. Because N has to equal 2 before L can equal 1. But these three orbitals are equal in energy. The three orbitals, the px, the py, and the pz, are all equal in energy. And we'll talk about that tomorrow. Now I'm going to teach you a word. When orbitals are equal energy in science, and I don't know why they use this word, but in science, when things are equal in energy, they're said to be degenerate. D-E-G-E-N-E-R-A-T, degenerate.
So they're all degenerate.
So they're degenerate orbitals. That means equal energy. Okay? Equal energy, degenerate orbitals. D-E-G-E-N-E-R-A-T, degenerate. Now, I don't know why they picked that word, because in normal English, if you call someone a degenerate, they're useless to society. They're just a degenerate. They're just no good. Okay?
I didn't know that they put out the P sublevel. They're all linked to each
Degenerate. I'm telling you, write it in. I'm teaching you a word. Okay?
They're all degenerative to each other.
They're all three of the p orbitals are degenerate. These three, they're just different. The only thing is, they're different orientation in space. Equal energy. When we say they're degenerate orbitals, that simply means equal in energy, just different orientation in space. Okay? And again, I don't know why English has two completely opposite definitions of a word, but in this case, degenerate means equal energy. So p orbitals is just, we get this shape, but again, this is just answers to the math equation. This is all based on high-level math, and so they get this shape, and so we're saying the shape is going to be around this. So on my second energy level, not only then do I have the S, but I also have my p orbitals. So I can have a p orbital, I can have a p orbital on the X, on the Y, and I can have a p orbital on, let's do green, the Z. So on my first energy level, I can have 2 electrons in this one room, in this one orbital. But on my second energy level, I have a bigger 2s, but then I have my 3 p orbitals on that sublevel. Now, how many electrons did I say can go in any orbital? 2. So I can put 2 into here, 2 into here, 2 into here, and 2 into here. So how many on the second energy level, how many electrons can I have on the second energy level? 8. 2 on the first, 8 on the second. 2 of them are going to be in the 2s. The other 6 are going to be in these 2p orbitals. Different arrangement in space. So if you don't like my pretty picture here, you can look at this pretty picture over here. This is neon showing its electrons, how the electron cloud is. And you have your 1s orbital down here, a little sphere. You got your 2 electrons buzzing around in it. Then you have your bigger sphere with your electrons all on the outside out here. And then you have your p orbitals, px, py, and pz. So neon has 10 electrons. 10 electrons, and those electrons look like, if I'm just looking at it from the outside, it just looks like it's one big cloud of blurry negative charge. But the reality is the electrons are very subdivided. They're very much in a given area based upon their energy. So I go to the third energy level. N equals 3. Now what can L equal? 0, 1, and 2. So what does L equals 0 always mean? What does L equals 0 mean? It's an S sublevel. What's the shape? Sphere. It's just going to be a bigger sphere. This is my 3s. But L can also equal 1. This is L equals 0. L can equal 1. So when L equals 1, what sublevel is that referring to? P. So on the third energy level, you can have a P sublevel as well. Okay? So on here, then, I can go, the only difference is it's just going to be bigger. And then lastly, we go here and here. Okay? So now I have, again, a space in between where there are no electrons. So you got electrons hanging out here, you got electrons hanging out here, but you don't have anything kind of in between. Because they can only go from one fixed energy level to the next. Now, when L equals 2, that corresponds to a D sublevel. Every time we go up, it gets a little bit more complicated. You can have 1 orbital on the S sublevel. You can have 3 orbitals on the P sublevel. You can have 5 orbitals on the D. 5 degenerate orbitals. What does that mean? 5 degenerate orbitals. They're all equal energy. The only difference is their orientation in space. So again, when you plug in the math, on these, you end up getting, okay, these probabilities of where we can find the electrons. So we just try to draw a shape and say it's a complex rose petal shape. That's what goes in the blank. Complex rose petal shape. When's the first time that n? When's the first value of n that L can equal to? 3. So they're only on the third energy level and above. Okay? So all these different shapes, there's all the different orientations in space. Again, but there's 5 different ways they can orient, but they're all equal energy. 5 d orbitals. But how many electrons can be in any orbital? 2. So even though these are bigger, still only 2, 2, 2, 2, and 2. So on the third energy level, we have an S. How many can be in an S? 2. We have the 3 P's, 2 in each for a total of 6, for now 8. But now we have the D's, 2, 4, 6, 8, 10. So how many electrons total are on that third energy level? 18. 2, 8, 18, just like you learned in middle school. But they're not in a ring going around the nucleus like a planet going around the sun. Instead, they're in these complex wave patterns in these orbitals where they most probable place to find them. Now, I can't draw that onto there. I'm not that good. Okay? I just can't I can't do that. But all of these would be superimposed on that. Now, n equals 4. N equals 4, we go to the fourth energy level. Now what can L equal? 0, 1, 2, and 3. So on the fourth energy level, we have 4 sublevels. Okay? Well, L equals 0 is an S. L equals 1 is a P. L equals 2 is a D. And L equals 3 is an F. Now, how many orbitals do you think are going to be on the F? If you can have 1 in the S, 3 in the P, 5 in the D, 7 in the Fs. Now we're not going to have time to get to, aren't we done at 3? Okay, we're not going to have time to get to the next quantum number, but the next quantum number just tells us why we can have 1, 3, 5, 7. Okay, the next 2 are a lot easier than this one. Okay, and then we'll finish this up tomorrow and start application of it and try to figure out how to actually write and draw these electron configurations. And the mic drop moment is going to be when you see that this entire periodic table is arranged based upon these S, P, D, and F sublevels. Okay, so it's kind of crazy. So it's going to make life a lot easier and not having to memorize, knowing how the periodic table is arranged. But all that is something we'll look at tomorrow. So for now, have a great day and go Jags.